So let us just see again our conventions and the symbols. So what does lowercase f denote? A force in the local coordinate system, and uppercase will denote the force in the global coordinate system, and same logic we use for the displacements. So for displacements we are using the symbol D. If it's lowercase d, that means we are referring to the displacements with respect to local coordinate system. That is here what is D3? D3 is essentially the rotation. And if we are referring to the global coordinate system, then we'll use uppercase letter. Of course, for this case D3 and this D3 they are same. Let's see how do we generate the total stiffness matrix of the structure. So we have, just by standard formulations, we have generated the stiffness matrix of an element. It could be beam, it could be column, it could be a truss member. That we can do. Now we have to generate the entire stiffness matrix, but not using the matrix stiffness approach, without any human intervention. So what we do in the next few slides, we will derive some general rules, I would say golden rules, by which we can write a simple program so that all these computations they are done automatically. So just pay attention, because this is a very important part of the section we are covering. So first of all, we assume that we have a simple 2D structure only. So we'll assume everything very simple boundary conditions, simple structure. We have 2D structure, and we assume that all the supports they are fixed. Those supports, they can have hinge, or there can be some other type of support, but right now for derivation purpose we are assuming that we have fixed support everywhere. Alright, and we have a frame with all rigid joints. There is no internal hinge, just like when we did some of the examples in the beginning, we introduced hinge inside. So right now we assume there is no hinge. So everything is made up of rigid frame. So joints, they can be numbered sequentially. We will follow horizontal numbering, or we will follow the vertical numbering. And we will number the joints such that the restrained joints, they are numbered at the end. So here we will be numbering the restrained joints also. We will be associating some kind of degree of freedom also with the restrained joints. Reason being that we want formulations which give us reactions separately. So one by one, after we derive the basic formulations, we will introduce the complications, like we will introduce support settlement, we will introduce internal hinge, we will introduce temperature effects, we will introduce non-prismatic members, we will introduce shear deformation effects. So all these one by one we will introduce. So for the time being, to derive the basic formulations, we are assuming very simple case. So this is our numbering scheme, that we will number either horizontally or vertically, and later on we will see which will give us a better option, that we will also see. So right now assume that we have numbered the joints like this, and N is the last joint. That includes the restrained supports. So now here is the difference, that when we determine what are the degrees of freedom, we will not say that only the unrestrained joints, we will include these also. So that's the small division we will be doing, and the reason is that we want reactions. Now we define our joint loads and joint displacements. Now earlier we were dealing with the member end forces and member end displacement. They were internal forces, they were internal displacements. Now these are the external forces and external displacements. We call them as joint loads, or we can call them as the structural loads and displacements overall. So we use the symbol P and U. So P for the forces and U for the displacements. So earlier we were using for the internal forces F, lowercase or uppercase, and internal displacements D, lower or uppercase. And we will be now associating each joint with particular degree of freedom. So now we can take advantage of the sequential numbering. So if we have the nth joint, what will be the numberings associated with forces and displacements? Yeah. So P3i minus 1, P3i minus 2. So that will be the numbering for the forces and similarly for the displacements also. Right. So forces and displacements, they follow the same subscript of the number. And then comes to the reactions. Now reactions will use the symbol X, but the subscript will refer to the joint number. The numbering we are following continuous. Means after we end here, which is a unrestrained joint. So when we start here, this is the next joint. So accordingly our numbering, we just replace the symbol P by X. That's all. But the subscript will have continuity because we have the last joint N. So we have X3n, 3n minus 1, 3n minus 2. That's the numbering scheme we adopt. So right now we assume there is no support settlement. So all the support joints, they are firmly restrained. So now we want to make a matrix like this. On the left hand side we have the force vector. So the force vector should include the external forces as well as the resulting reactions, both of them should be there. And similarly we have here the displacement vector. So we can do a partitioning. Somewhere around here we can do a partitioning where all the P terms they finish and all the X terms they start. Below this we have all the reactions. So in short we call this system like this, that this we call as P vector, this we call as the X vector, the unknown reactions. So P is basically the set of the known forces. We say prescribed forces. They are prescribed forces. And on this side we have the displacements. We can do partitioning here also. So we have here UP, which are the unknown displacements now, and we have here UX, which are the prescribed displacements. And this number should be, the last number should be UX 3n. And 3n refers to the number associated with the degree of freedom. So that way we do the partitioning, and we call this matrix this as KPP. We call this as KPX, we call this as KXP, and this KXX. So that partitioning we can do. And now what is the relation between KXP and KPX? They are transpose of each other. Now let's consider a particular joint. Let's say this is the I joint, and we find what members they are meeting here. There are three members here which are meeting here. Let us now apply a unit displacement along the degree of freedom 3i minus 2, which is the horizontal displacement here, such that all other degrees of freedom and the corresponding displacements, they are restrained. So we have to apply a force in this particular direction. This is how the members A, B and C will undergo deformation. Now let's go further and let's form the system where we can see the internal forces also. Free body diagram. Now this is the joint. So we have opened up all the members. There are three members, A, B and C, and this is the I joint. So we know what are the forces acting here, what are the displacements, and then we have opened up this joint to see the internal forces also. Alright, so we have here this member B is the joint. This side is I, and this side we have joint J, which happens to be one increment higher, because we are numbering sequentially, horizontally. What we see here? We see here the external forces also, and we see here the internal forces also, and internal displacements also. We have shown here the degrees of freedom. So now we have to find out the correlation between the two. If we establish the correlation in such a manner that we can write a simple program. Now you see here member number A, we are showing here 6 numbers. So they refer to internal displacements, internal forces. Now all these numbers, they are with respect to the global coordinate system, not local. Similarly, we have member number C. We have 1, 2, 3, 4, 5, 6. So they are referring to the global coordinate system, global X, global Y and global Z. And we have member number A. So we have 1, 2, 3 and 4, 5, 6. Now which will be 1, 2, 3, which will be 4, 5, 6? That is a subjective matter. So it depends on which joint you are assuming as the first joint and which joint you are assuming as the second joint. So its choice is yours. So we call these as the structural degrees of freedom. The degrees of freedom which are associated with joint and which are related to the external forces acting on the system, we call them as the structural degrees of freedom. And all these degrees of freedom 1 to 6, their range can be only 1 to 6, and they are the member degrees of freedom. So we have the member degrees of freedom, they refer to a particular element and they can be from 1 to 6. And whereas the structural degrees of freedom, they depend on the joint number. So we have here 3i, 3i minus 1, 3i minus 2, and this side we have 3j, 3j minus 1, 3j minus 2, where j we assume is the next joint, next to I, so it's I plus 1. So each member degree of freedom in the global coordinates, that is 1 to 6, it corresponds to a particular structural degree of freedom. You agree? Basically we have here all these numbers. So all these numbers, they will definitely correspond to some structural degree of freedom. So basically we have to adopt a relation between the two, that is called as the code number approach. So that's what we'll derive here. So let's say we have this degree of freedom, this displacement, a translation along 3i minus 2 at this joint I. So which members they are involved? All the 3 members they are involved. So that means this displacement essentially corresponds to this particular degree of freedom for member number C, which is 1. And for member number B also this is degree of freedom number 1. But for member number A, this is degree of freedom number 4. How these should be related? They are one and the same essentially. It's just the numbering scheme. We refer to either the members or the structure. So the answer is that they are related by 2 conditions. One is the compatibility and other is the equilibrium. You agree or not? So how they are related from point of view of compatibility? Joint is a rigid joint. So when there is a displacement acting at the joint, what will happen? We know that the joint is rigid. So all the members, they will undergo same amount of displacement at that particular joint in terms of both the translation and the rotation. So we can write this in form of equation and using the symbols. So we can write this like this, that u 3i minus 2. What is u 3i minus 2? It's the joint displacement. And from where 3i minus 2 comes is because this degree of freedom is 3i minus 2 is the translation. So this must be equal to the corresponding displacement of all the 3 members. So we have member number A. So this is D4 because this is the 4th degree of freedom. Member number B is the 1st degree of freedom. And member number C is again the 1st degree of freedom. So this is the compatibility condition. Now what is the equilibrium condition? How do we apply an equilibrium condition? What is the relationship between external and the internal forces in the case of equilibrium at a joint? We use that in the moment distribution method and also in slope deflection method. In slope deflection method, how do we achieve equilibrium condition? MBA plus MBC equal to MB. That is the external moment should be equal to the sum of the internal moments of the members meeting at that particular joint. So same logic we can apply here.
These moments are joint moment or member moment?
This is joint moment and all these are member moments. These are member forces, these are internal forces, these are the external forces.
Sir, for member moment, sir, you have considered anti-clockwise movement positive. So for here, for joint, you should consider clockwise movement positive.
No. Our symbol is anti-clockwise positive, whether we member or the joint. Alright. So now this confusion I will just resolve that, let's say from the point of view of the joint equilibrium. Do you agree that MB should be equal to MBA plus MBC? Yes. So how it is happening? Because on the joint, opposite of this will act. MB is acting on the member. So on the joint, opposite of this will act. And here also opposite of this will act. So now you do equilibrium of the joint. Do you get the same answer? So if you do joint equilibrium, you get same answer. So that means we need not draw the joint equilibrium. Just that whatever is the direction of the joint moment, the internal moments on the members, they should be in same direction. That's the common thing we use in the slope deflection formulations. Okay, so now next is the equilibrium equations. So equilibrium, what we do, let's apply a unit displacement along this particular degree of freedom and keeping all others locked. So we are little bit using the techniques of the matrix stiffness approach so that we derive something for the direct stiffness approach. So we are applying a unit displacement along this joint such that we have unit translation here, but all other degrees of freedom are locked. So that means we are achieving something like this. So now by definition, what will be this force? What force will be required here by definition? But we have defined what is Kij, and here we are applying a unit displacement. This is a unit displacement. So if we go by first principle, what will be this force? 20? Okay, let's not go into the value. Basically, it's some term of the stiffness matrix of the entire structure. So what is that term? Kij. So what is that I and what is that j? This is degree of freedom 3i minus 2. So basically it's k. Yes, exactly. It's k 3i minus 2, 3i minus 2. Right? It's the diagonal term. Okay. So we have applied unit displacement along this particular degree of freedom. Now I have broken it down. So by joint equilibrium, whatever force we apply here, it should be equal to the sum of the member end forces A, B and C. Right? And in the same direction. We are talking about the member end forces, not the joint forces. So this, you agree? This should happen just like for the case of the moment, MB is equal to MBA plus MBC. So same logic applies to the horizontal and the vertical forces also. But what are these forces? We applied some force here, and then what we find that as a reaction here, these forces they are generated. So what are these forces equal to? We can use the nomenclature we have chosen, that these are equal to, remember what convention or what symbols we are using. For member number A, this is F4 of member number A. This is the fourth component. For member number B is the first component, and for member number C is the first component. You agree? But then what is this P3i minus 2? We have just now asked the question and we have responded. This is basically, by this definition of the Kij, this is the term of the stiffness matrix, because we have applied unit displacement. So this must be K 3i minus 2, 3i minus 2, this particular force. Agreed? Now what should be this force? F4A. F4 of member number A. Remember that member number A is also undergoing a unit displacement. So how the displacement is happening? It's also undergoing a unit displacement. So it has undergone some displacement, but that displacement is unit. So what should be this force equal to? Not with the value, I don't want the value. Yes, because by definition it has moved only by a unit distance. So this force must be equal to K for 4 of member A. So it must be a term of the stiffness matrix of this particular member A. And similarly, what will be F1B? We see that it's an axial component. So what in terms of the stiffness, which element of the stiffness matrix of element B this term should be? It should be K11B. And then third, we can just extend the logic. This should be what? K11 of member C. All these members A, B and C, they are framing at this particular joint, and they may have different values of the various parameters and various elastic constants. That may happen, and you can find out these values because we have standard expression for these terms. But we have derived something very important in the process. What is left hand side? Left hand side, we have the element of the structural stiffness matrix. And on the right hand side, we have the stiffness matrices of the individual members meeting at that particular joint. So how do we relate the two? We have derived very important principle now in this connection. So the principle is that an element of the total stiffness matrix of the structure is basically algebraic sum of some of the elements of some members of the structure. But which are those members and which are those elements which are to be added? It's not arbitrary. That means in this term, these particular elements, they have made contribution. Only these members. Other members, they will not make any contribution. So we can write it in this form, that an element of KTS means total structure stiffness matrix, can be obtained by summing the elements of member stiffness matrices in global coordinates of corresponding degree of freedom from members that frame into that joint. That's the important thing, that we have the degree of freedom from the global point of view 3I minus 2. So first of all, we have to find what are the corresponding member degrees of freedom. Which members have that particular degree of freedom, and those terms, all those terms, they will contribute to that particular element of the total structural stiffness matrix. So this is the golden rule. No other element will make any contribution, because when we have applied unit displacement at a particular joint, what we have done? We have locked all other degrees of freedom. So only the members which are connected to the joint, they will deform, and as a result, only they will contribute to something. Other members, they don't contribute. Right? So this is the central part of the direct stiffness approach. Because by making use of this, we don't have to physically see which members they are contributing. So program can do it itself by code number approach. So we call this approach as the code number approach. So we follow this method. So we'll explain it further. So what happens is that each member degree of freedom, it corresponds to a particular structure degree of freedom. So essentially only those elements, they may contribute to the total structure stiffness matrix, and no other contribution is there. Like here we see that in general this is the joint, and let's say we see this member B. It has two sets of degrees of freedom. One is the member degree of freedom and the other is the structure degree of freedom. So member degree of freedom is from 1 to 6. Now what will be the structure degree of freedom? At this end we have joint number I, this end we have joint number J. So our degrees of freedom should be like this. And they are one and the same. One is the your member degree of freedom, other is the structure degree of freedom. We have joint here I, so we have 3I, 3I minus 1, 3I minus 2, and other side we have joint J, so we have 3J, 3J minus 1 and 3J minus 2. Right. So we can store this information in a matrix which is called as association matrix. So we define its association matrix like this. So what are the various elements? We have 6 elements. 1, 2, 3, 4, 5, 6. So that means the member degree of freedom number 4 corresponds to structure degree of freedom 3 bracket I plus 1 minus 2. Just check physically, is it okay? This is the 4 degree of freedom, this is corresponding to this degree of freedom, correct? Physically also we can verify. So this matrix is called as the association matrix. So what our program should do, it should form association matrix of all the members and store the information here. Then we are very sure that where a particular element of the stiffness matrix of the member, it corresponds to what element of the total stiffness matrix. That means, for example, let's say this is 3 and this is 4. So that means K34. K34 of K of this member, it corresponds to 3I plus 1 minus 2 of KTS. Right. So what is this? This is the correspondence between the member terms with the structure terms. And what we have made use of? We have just made use of the subscript. And subscript information we are storing in this particular matrix. Alright. So let's say this example. Here we have a 2D structure of frame. So what will be the size of KTS? We have total 9 joints. So 27 by 27. So let's just write here 27 by 27. So what our program will do? Program will know that okay, the last joint is 9. So the total structural stiffness matrix should be 27 by 27. And if we are just referring to some member, let's say this member, and let's say we have the stiffness matrix of this particular member. So now we have this matrix 6 by 6 for this particular member 3. So we call it as K3 global of member number 3. Now the point is where these elements they go here. Because we say that essentially an element of KTS, it is the summation of the elements of the members which are framing at a particular joint, and they will contribute to that particular degree of freedom. Let's say we have this joint number 4, so here 3, 5 and 6 will contribute. So we have to find first of all one by one this member number 3 where this contribution is landing. Then we consider member number 6 where its contribution is landing, and if there is some element already there, we add to that, and then where the contribution of member number 5 is landing, and we add to that. So let's see this member number 3. Now my point is where these will go. So first of all we have to form association matrix of this member. So what will be the association matrix of this member? So A of member number 3. How do we find that? We have to see what are the its structure degrees of freedom and the member degrees of freedom. So I draw here both the member and the structure degrees of freedom of this particular member. So let's say here I want to draw the member degrees of freedom, and just adjacent to that I want to draw the structure degrees of freedom. So just keep me dictating the values. What will be the member degrees of freedom here? 1, 2, 3. Everything with respect to the global coordinate system. Global coordinate system is like this. This is your global x-axis and this is your global y-axis, and global z-axis is towards you. 1, 2, 3, 4, 5, 6. Now what are the structure degrees of freedom? Here joint number 4, joint number 5. 4 means last should be 12. 12, 11 and 10. 10, 11, 12, right? So we have 10, 11, 12. And on this side we have 5, that is 15. So 13, 14, 15. So this is understood? So that means what will be the association matrix? 6 elements we have to write in this association matrix. 1, 2, 3, 4, 5 and 6. So what will be written in the association matrix? 1 corresponds to 10. So we write here 10, 11, 12. And what else? And what will be the next 3 terms? 13, 14, 15. So just by chance, because it's a team element and the numbers are also sequential, so they are always consecutive. But for columns it may not be consecutive. Columns we don't have this sequential number. We have gaps. So now we can write these numbers here. So now we have solved 90% of our problem. So if I ask you question, where will this element go? K, the first element, where will it go? Yeah, it will go to 10, 10. Right? So where is 10, 10? It will go here. Where will this element go? For example, K4, 3. Where will K4, 3 go? 13 and 12. Right? It will go to 13 this side and 12 is here. So similarly, we know that where each element, when we say a particular element of this is some of the elements of the stiffness matrix in global coordinates of the members forming in that particular joint and having the corresponding degrees of freedom. So now we can do it. We know. So we can do this for all the elements. But then we have to do it for each element. We cannot take advantage of symmetry here. We have to check all these. Symmetry we have to see for this KTS. We say that okay, we will only form the lower triangular half. So if we find that an element is going to the upper triangular half, we don't send. Right. Like for here, the maximum is 15. So some elements they go to the upper triangular part also. But majority of the elements they land up in the lower triangular part. So we have to check for each and every element. We have to repeat this process 36 times. 6 by 6. Each element 1 by 1, 1 by 1, where it will land. So we will basically be concentrated into this particular zone, that majority of the elements they are in the lower triangular and some elements in the upper triangular part. So this way we can establish a direct correlation between the member stiffness matrix terms with the total structure stiffness matrix terms. So we have to do this one by one. So let's say this, we have for example here the degrees of freedom are 12, 11, 10, 10, 11, 12. So these 3 elements will contribute. These 3 elements will contribute and corresponding to these degrees of freedom. Just like we have done for member number 3, we have to similarly do for member number 6 and we have to do similarly for member number 5. So we keep on doing this. When we repeat for the all members of the structure, what we get? We get the final total structure stiffness matrix. So what we have done it? We have done it computationally. We have not used any crystal class. So we stop here and we'll continue further in the next class. But do a homework exercise. I give you the job of finding the element 99 of KTS. So by forming the association matrices of the members, find out first of all which members will contribute to this particular term and then which particular elements of their stiffness matrices will land up in this particular element 99 of KTS.